Good morning, everyone, and thank you all so much for being here. Today, I want to start by inviting you to think about the many ways in which we interact with structured data in the real world. Our world is filled with information presented in structured forms. So take a look at these images, right? Whether it's an insurance bill or a flight schedule at the airport, or a restaurant receipt, or even a school timetable in your child's notebook, tables are everywhere. And all of these examples, they contain data that's structured in a very specific way to communicate meaning effectively. Structured data isn't just limited to tables or receipts. It's also in the visualizations we encounter in the media. So here are some examples from the New York Times. And these charts take data, whether it's sports or climate or price of goods and everyday costs. These charts take this data and represent it visually. And notice how each element, color, size, and position is carefully chosen to convey meaning. And these details help us to quickly interpret complex information. Believe it or not, structured data extraction applies to even the things we wear. Take this sweater, for example. At a first glance, it may seem like it's just another garment, but it actually encodes highly structured programs. On the left, we see the original sweater image, which is the designer's vision. But to bring this vision to life, the designer has to convert it into a program that's seen here in the middle. And this program is coded blueprint that tells the knitting machine how to perform each stitch. So each color and symbol in this program represents a different type of stitch or pattern. So for example, the front knit and back knit stitches dictate the texture and structure, and then the tuck and split, they add some patterns and variation in the fabric appearance. So each stitch type acts like a building block or primitive. And by combining these primitives, we can control the overall texture and color and shape of the sweater. So on the right is the machine, the knitting machine in action, which is actually executing the program. And the machine follows instructions line by line in this image here, stitch by stitch, and it tries to recreate the original design. So with the program, you can faithfully reproduce the vision that you saw in this original image into an actual sweater. And this technology isn't just limited to sweaters. These principles are also applied to high-performance products like footwear and spacesuits for astronauts. So here is Deva Newman showing off the 3D knitted biosuit design for astronauts, which is very cool. It's a TED Talk. I would encourage you to watch it. But what happens if there is an error in translating the sweater's design into the knitting program, right? The machine might misinterpret the instructions, and instead of a cozy sweater, you end up with something that looks like Swiss cheese. So when I first ran my knit program with some complex patterns, I noticed that certain design elements didn't come out as I had planned, and the machine produced holes in the fabric because it misinterpreted parts of the program. Interestingly, my program was syntactically correct, and it ran perfectly on the machine, but there were some semantic errors in my code that I hadn't noticed. And these subtle mistakes affected how the machine understood the design, and it resulted in a flawed final product. And so what this experience really highlights is that there's a very big importance of precision in the translation process. So even a small error in the program, especially at the semantic level, can completely alter the outcome. And the same level of precision is essential when we extract data from images. So for example, here is the ground truth chart showing different basketball players and their performance by age. And what happens if you accidentally swap out the player names or age? You will have a completely different interpretation of the player's achievements, and you might turn legends into rookies, right? And the same goes for extraction from table images. So take this flight schedule example. Below are the first 5 rows that are extracted from the table image. So what do you think is wrong with this extraction?
Does the pattern instead of landed? Or it's swapped? It's swapped the pattern.
It's swapped, right? So all the arrivals are basically extracted under departures, and the departures are extracted under arrivals, which is very problematic because people will miss their flights. And so what types of errors can we expect when we extract data from table images, right? So we can make structural errors. So here's an example of an incorrect structure. So here is the ground truth structure, and here is the incorrect structure. So what happened was that this HTML had the wrong column span in the first row, and it also missed a cell here, which resulted in all the cells in the first row and the cells here to be shifted to the left. Right? So here's an example of a structural mistake. But you could also end up losing content because you missed a cell. And so you can also have content-related errors when you extract data from tables. Moreover, preserving spatial relationships is important. So when we swap the departures with arrivals, what happens is that we lose the relationship that this particular content belongs to the departures and this content belongs to the arrivals. And so even though all the content was extracted in this case, the meaning of the table has significantly changed, right? And so subtle errors can lead to large misinterpretations. So over the years, several methods have been developed to tackle this problem. And I will walk you through all the various table extraction methods and how they have evolved. So one early deep learning method was DeepDSRT, which basically brought object detection to tables. And what this work did was, just like identifying objects in a busy scene, they used a FastRR CNN with a VGG16 backbone to detect tables and columns in an image, and combined with an FCN network to predict the structure. So let's look at how it did that. So here's a sample scan document with a mix of tables and text. So the particular tabular structures that you can see here are up here, and these three tables here, right? And what the FastRR CNN does is processes this image and makes a bunch of region proposals for what might be tables. And then the classification step tries to classify each bounding box as whether it belongs to a table region or not, right? And then we use an FCN model to train for row and column segmentation. And so what you get is a bunch of bounding boxes telling you what the rows are, and then vertical bounding boxes telling you what the columns are. Now here's an example where DeepDSRT fails. And as you can see, that it specifically struggles when the table has a lot of nested and hierarchical structures. So for example, look at the first column, sample group, right? This column has 3-year-old and 4-year-old, and that's further nested down into the different groups, the control groups. And so for such a scenario, the object detection idea struggles because it's optimized for more simpler, straightforward tables that don't have many hierarchical structures. It also struggles when the rows and columns are very close together. So take a look at the first image here. Because these two tables are very close to each other, the boundary for the first column was misinterpreted as the beginning of the boundary for the second table. And similarly, when there's no lines, when no border lines are present in the table and you have to detect the rows, you see how the model predicted this entire segment as a row. And so when rows and columns are closely spaced together like this, and when there are no boundary lines, it becomes very complex for something like DeepDSRT to process. So traditionally, table and column detection were treated as two separate problems, which often led to a lot of false positives in column detection. And so the next model that I would like to introduce you to is the StableNet model, which proposed an end-to-end detection for tables and columns. And what this model did was it unified both the detection of the table and the columns simultaneously. So the architecture is based on a classic encoder-decoder setup. So here they have a VGG19 backbone and an encoder, and then two separate decoders, one for table detection and one for column detection. And another fundamental difference in this work is that instead of operating over bounding boxes, we're now operating over pixels, which are more robust to noise, right? And this is especially important for tables because you cannot make tables are not very robust to mistakes because you could easily swap out two columns with each other. So step one is the image goes through the encoder and generates like a mask for the table detection. And then the decoders basically detect the mask for where the columns might be. And so once you have these masks, you have an off-the-shelf OCR extraction model, which tells you where all the text boxes are. And then you use these masks to filter out the text regions that are within the table region. And then you have some sort of heuristic for row extraction, where you only keep text regions which are from different columns but around the same Y value as to be one row. And then suppose you have a row that has multiple lines of text, then you would always start a new row when you only have non-blank cells in the row. The major drawback of the work is that this requires a lot of annotated data. So the input to the model is a tuple, which is an image with all the text boxes color-coded, and these color codings are based on the data type of the text. So this is a very interesting way of adding additional semantic knowledge to the image of what the content might be, but it requires ground truth annotations of the masks as well, which is very difficult to obtain. So the next model that I will introduce you to looks at how you can use unsupervised learning to help eliminate this problem. So recently, this work called Unitable proposed a self-supervised pre-training approach. And here the model learns tabular representations without any labeled data sets. So the goal of Unitable is to basically take the table image and convert it into a machine-readable sequence of HTML tags or bounding box tags or content tokens. And the core essence of this work is the pre-training fine-tuning paradigm. So a self-supervised visual encoder is pre-trained with lots of tabular images, and then the model is fine-tuned on these three separate tasks. And then that result from these three tasks are combined into a table. And I will walk you through how that happens. So, but I'll just pause to see if there's any questions so far. Okay. So Unitable essentially operates on the VQ-VAE framework. You first start by defining a visual codebook, which is a set of discrete tokens, and you split up the image into these small patches. And during pre-training, the task is to train an encoder which predicts a token for each of these patches. And then in the decoding step, takes the image with the patches and the tokens predicted and tries to reconstruct the image. And so the optimization objective is to reduce the error between the reconstructed image and the original image. And so what we end up with are patches which look like this after training. So as you can see, that like similar group of tokens will appear in similar regions in the image. And so here is an example where each patch is encoded as a discrete token from a codebook, and you can see that they semantically represent relevant areas. So for example, this image shows how these red patches are all background patches. And in this one, you can see how the red patches all have the same tokens, and they're always around the boundary lines, which is quite interesting. So now, without any label data, you have encoded a lot of semantic information about tables and the different nuances of tabular representations into this codebook. Okay. So once the visual codebook is trained, the model is further tuned using masked pre-training. So what happens here is 40% of the patches are randomly masked out, and the optimization objective is to maximize the log likelihood of the masked region. And this way, the model learns how to predict tokens for each of the patches of the images. And so by learning how to assign the highest probability to the correct tokens in these masked positions, the model is learning how to capture the underlying patterns of the table structure and layout. So now, after pre-training the encoder, we now have learned rich semantics about the table images. And so the next step is to integrate the model's self-supervised visual understanding with a structured decoding process. So each of these three decoders are trained to take the patched images and predict the next token sequence. So in the first task, the table structure decoder, the task is to predict HTML-like tags. And these are tags without any cell values, but just placeholders for these values. And the cell bounding box decoder predicts a sequence of bounding box tokens. So these are the corners of the cell box. And the third decoding task is to predict the content of each of the cells. And the result from these three decoders are incorporated to predict the entire table image. Okay. Any questions so far? Okay. Great. So Unitable turns out that it fails on real-world camera-taken images. And this is because the pre-training data set contained a lot of synthetic table images, and so it was not able to generalize to these kinds of tables. And so one way to improve Unitable's performance on these real-world images could be to just fine-tune the pre-trained visual encoder on these sets of images, and then retrain the task decoders, and perhaps the model would work better on these cases. But even with these improvements, we're still primarily relying on visual information alone. And I think that to truly understand the complex, messy tables from the real world, we might need more than just visual cues. And maybe things like LLMs, like GPT-4 Omni, encode a lot of general purpose information about tables. So why not see to what extent we can leverage them? So this summer, I decided to investigate to what extent can LLMs extract tabular data from images. And I wanted to see whether we could solve this problem at just inference time without any fine-tuning. So for the baseline prompt, I gave the image of the table to the model, and I asked it to extract the HTML for the table image. And I ran this experiment on 800 images from TableRec and 800 images from SynthTabNet. So TableRec is a data set with a lot of messy real-world looking like tables, and SynthTabNet are images, table images from synthetic LaTeX and PDF tables. And the scores that we see here are F1 scores. And what I found was that the model performed reasonably well to some extent. But what happened with the 10 to 30% of images that failed? So for this input image above, this was the prediction of the model below. And what you can see is that first, it has swapped out all the rows and columns. It has transposed the table. And second, it struggled to predict all these numeric values. So it's missing a lot of content. It also fails to maintain structure. So here's the input image, and here's the output from the LLM. And as you can see, that the row span for this particular cell is one less than it should have been. And it also makes some span errors for these two cells. And so what this suggests is that there's different error sources in both of these cases. And sometimes the model struggles with structural reasoning, and sometimes it has inadequate OCR extraction. And so perhaps one way to solve this problem is to separate the strategies so that you can get a better accuracy. So here's an example of a table. It's a very simple table. It has both visual and semantic content, right? So the visual aspects of the table are that there's 24 rows and 2 columns, and there's dark blue text. It's handwritten by a teacher and student, and so on. And the linguistic features of this image are the various data types of the columns, the fact that these are question-answer pairs, the fact that this column is categorical data, and so on. So there's different types of features embedded in the image. So let's try to disentangle these two aspects of reasoning. So one way could be to separate the steps using chain of thought. So the prompt that I gave to the model was to first extract the structure, and then extract the content, and then turn it into a table. And what we found was that the performance slightly drops from baseline when we use chain of thought. And content is even worse. And maybe it's possible that the model conflates the extractions during each of the steps. So I thought, why not disentangle the task entirely? So instead of doing chain of thought, why don't we try to do table structure extraction separately and table content extraction separately? And so to run table structure extraction separately, I asked the model to look at the image and just give me the HTML structure, the template of the image. And what we found was that it got about 68% correct, which is still worse than baseline, which is strange because I would have expected this to be higher. And then for OCR, I passed this prompt to the model, and I asked it to extract the OCR content from this. And we found that the OCR was comparable to the baseline. And then the next step was to combine both of these into a full table. So the input to the prompt was the image, the extracted text, and the structure. And the task was to combine these two elements into the full HTML table. And so with just this step, we found that the performance was 70% and 42% for structure and content. So this is still not very impressive, right? And so you would think that perhaps we need to ask the model to self-reflect and refine its outputs. And so for the review step, what we did was we asked the model to take a look at the rendered image and the ground truth image and provide feedback on what might be the different errors that the model was making in this step. And what we found in this process was that sometimes the model would hallucinate on what the feedback should be. So even when there were no errors, it would try to hallucinate some errors. And then we would provide the feedback and the HTML template to GPT-4 Omni again and ask it to rectify the original structure. And so with refinement, we saw a slightly improved performance without refinement, but still very comparable to baseline, not impressive. So we also tried this approach with charts. So here's an example where this is the ground truth chart image. So what we did here was we passed the chart image, run it through the DVLR pipeline, ask it to predict matplotlib code, and render the chart image back. And for the baseline prompt, what we saw was that it was actually missing a lot of the data points, and also it mispredicted the locations of the different scatter points. With chain of thought, it completely hallucinated all the points. But with DVLR, we saw a reasonable performance where we saw similar looking points. So while DVLR is not phenomenal in its results, I think what's interesting here is that even without fine-tuning and with just inference time prompting, we can still get approximately 86% of correct tables extracted from images. And there's definitely promise, and perhaps what needs to be done is to improve the semantic precision at inference time. Another thing that can be tried out would be fine-tuning and have richer multimodal pre-training, and possibly having a human in the loop, because human feedback is like the upper bound on versus the feedback that we got from LLMs. And so that's all I have for my slides, but what I would like to leave you all with is that tables and charts are very special kinds of images because they encode both visual and text content in them. And most vision language models, the input data that they work with are visual question and answering style of models where the image and text are separate from each other. But for these cases, the text is ingrained in the image itself. And this requires new kinds of approaches and methods to innovate. And so that's all for my talk. Thank you so much.